That was my hope and intent to start getting caught up and getting these things back to you so that we can, believe it or not, get towards the end. And it's still a ways off, but it'll come quickly, as you well know. And so, looking at where we are then, as you know, we were on chapter 10. And what I said is it was a long chapter, or is a long chapter. And so we finally got through it, although what I didn't get a chance to do was to do any examples for you. And kind of torn because we need to move into chapter 11. But this morning I got to thinking about it, and I go, well, let's at least spend the first hour doing examples, and maybe even longer than that. We'll call it, play it by ear here, but no more than an hour and a half for sure, so that we can then get into chapter 11. And so chapter 11, as you will see, is more on this rotational stuff, but it's a short one. There's one last piece here that we did not do. And if you remember, we did an analogy. Everything that had translational motion, we had rotation. The exception so far has been momentum. We had linear momentum, but we haven't yet talked about rotational or angular momentum. And that's what chapter 11 is. So that's a long piece of topic in itself. So I kind of see why the author separated that one off, although I think moment of inertia is actually even a little bit harder, but you got to put that one into that chapter. So if you recall, we did a lot of calculations and a lot of time with the moment of inertia. Well, that being said, I thought we'd go ahead and start with number 4 as our first example. It takes us all the way to the beginning of chapter 10. It's a kinematics one, and it is one, as I said, that will show us then what I was trying to say is read the problem, and as you study the problem, then ask yourself, how would you do this in terms of translational motion? And once you get it in terms of translational motion, I think that helps a lot, because then you will then do the same thing but with rotational motion. And so going to the beginning of these problems, right about here, at 140%, where is number 4? It looks like number 4 is divided on 2 pages here. And so I'll read it. But I think you'll notice right away it's just screaming kinematics, kinematics, kinematics. And that's what I want you to notice here. First of all, it says a centrifuge is a medical, in a medical laboratory, rotates with an angular speed of. Okay, now maybe I'll stop here. You got to know a little bit about what a centrifuge is, but it's where we put the little test tubes in and it spins around and it separates the heavy stuff and the light stuff depending on how long you leave it there and how fast it's spinning. But clearly then, the first thing that hopefully goes off in your mind is this is a rotational problem. And you'll see that as we get to the next test and the final exam. One of the first questions you'll have to ask yourself, which, as you noticed on the second test, was what kind of principles am I going to use to solve this? Do I solve this with momentum? Do I solve this with energy? Is this a kinematics problem? And those are the ones we've done in the past. Now we have to start asking ourselves, is this a rotational problem or is this a translational problem? Or perhaps is it both at the same time? And we haven't really done those yet, but that you can see is what is coming up here as we continue along here. And so this one is clearly a rotational problem. That's the first thing that goes off in my mind as I do my mechanics. What type of mechanics am I going to do? And I'm going to focus on rotation. There's no translation here. It's just a little machine that is spinning. And so they say here it spins and it rotates with an angular speed of 3,600 revolutions per minute. Now there's an interesting part right there, which takes us back to the analogy of chapter 1. That's unit conversion. This is not radians per second, as we talked a lot about with speed. This is rotations per minute. And so I suspect right away that not only is it a rotational problem, but it's also a unit analysis problem. I've got to probably convert my units. Then it is switched off. It rotates through 50 revolutions before coming to rest. Find the constant angular acceleration of the centrifuge. Okay, so the good news here is they have told me it is a constant acceleration. And so the first thing that goes off in my mind is all of these kinematic equations that have the same form as our constant translational acceleration we wrote out at the beginning of this chapter. Let me just write them again. This was the first one. The second one looked something along this line. The third one was the one that we had argued is solving this one for time and put it into here. You get there. And the fourth one was what we got when we solved the first one for acceleration and put it into there. So there were our four kinematic equations. That's what goes off in my mind when I read this first one. That I do have a constant acceleration. They make it very clear. Find the constant acceleration of this centrifuge as it goes through 50 revolutions before coming to a stop. Also, as I look at that problem, I notice that not only can I use any one of these four, but chances are number 3 stands out to me just like it did back in chapter 2. This is the one that doesn't have time in it. Now granted, you could solve number 1 for time and plug it into number 2, but that is how we got number 3. So I'm going to jump right here to number 3 and then write it here. The constant speed, or the speed squared, final speed squared, is equal to the initial speed plus 2 times the acceleration times the distance traveled, or in this case, angle rotated, since we're talking about rotation. And so looking at this, I guess the first thing I would do is put in here a 0, because it says, you know, how or what is the acceleration is what we're looking for. Find the constant acceleration when it goes through 50 revolutions and comes to a stop. So the final speed is 0. Now the initial speed they have written down as 3,600 revolutions per minute. But I'm going to do some unit conversion. In place of the word revolution, I am going to put 2 pi radians. That's what 1 revolution is. And in place of the word minute, I am going to put 60 seconds, since that's what a minute is. And so I'm going to do a direct substitution. So in place of the word revolution, I will put 2 pi radians. In place of the word minute, I will put 60 seconds. So that would be my unit conversion for using rotational quantities. And so you can see this is analogous, hopefully, to chapters 1 and 2. So there's the beginning speed. Then I've got 2 times the acceleration that I would like to find. And again, it says after 50 revolutions. I'll put the word revolution, but I'm going to do the same thing and do a direct substitution. Everywhere I see the word revolution, I'm going to put 2 pi radians. I'm just going to substitute, right? And again, maybe it's worth repeating what we said from back in day 1. Treat your units like you do with your numbers. If you wanted to, you know, if you had some equation that said x equals 7 and there was an x in your equation, everywhere you see an x, you can replace it with that 7. So same thing here. Every time I see the word revolution, I will replace it with 2 pi radians. Well, then it's just a matter of arithmetic, or some algebra, I guess I should say, in order to solve this for alpha. And so I'll start here, 3,600 times 2 times pi divided by 6d and square that. All right. I'll bring it to the other side, so now it is negative, and in my case I'll just go times a -1. All right. Then I can divide that by a 2 as I bring that over. I can divide that by a 50 as I bring that over. I can divide by another 2 when I bring that over. And finally I can divide by pi. And so I get a -226. And of course now I want to look at my units here. But it looks like once I squared that, I got radians squared and seconds squared. And when I divide by a radian, then this would be radians per second each second. And of course, the negative would imply it slowing down if you're willing to accept that the beginning speed, there it is a positive number. So to slow something down, we need an acceleration that is opposite to the direction it is rotating. So I picked the direction of rotation as positive. They don't really say whether it's clockwise or counterclockwise, and so it's my choice. Of course, it's my choice to pick a positive sign for clockwise and counterclockwise. I know counterclockwise is our traditional way of calling positive, but who knows? But that's obviously what I picked. So clearly here at the beginning, I picked the initial speed to be positive. And because I did that, then the acceleration has to be negative, has to be opposite. But then again, that's kind of what we would have expected. So like I said, I thought that would make a good first one. Let's move on then in the short time we have. Let's go to 35. Again, if you remember, we did kinematics at first, and so you'll have your share of kinematic problems there on the homework. And then we looked at kind of that connection between things rotating and translating, that if we had something going in a circle, we could look at its translational speed as it goes in its circle, or we could look at its rotational speed. And I think that's illustrated here with number 35 really well, is that it does look at an object going in a circle and allows us to look at it in terms of translating in a circle or rotating, and we can interchange one and back and forth between the others, whichever it is useful. And then of course, then the problems got a little bit harder after that. But I'll start here with 35 here. It says a model airplane with a mass of 0.75 kilograms is tethered by a wire so that it flies in a circle of 30 meters in radius. All right, so maybe looking from above, an aerial view, maybe there is this long wire here, which they say is 30 meters, and then we've got this airplane at the end of it flying in a circle. And so that's what they mean here at that first sentence, airplane tethered, flying in a circle. Maybe I'll even put the mass up here so that I don't forget, but they said it was 0.75 kilograms as the airplane flies in a circle. Okay. The airplane engine then provides a net thrust of 0.8 newtons perpendicular to the tethered wire. Okay, so the free body diagram, maybe I'll just grab a different color here, but what they're saying here is there is this thrust, and they don't really say which way the airplane is going. Maybe I'll set it up so that the airplane is going in a counterclockwise direction. And of course, like I said, we probably could have picked any direction for that. They do say, if you look carefully, net thrust. And so that means as it moves through the air, there's a combination of the thrust from, say, the little propeller it has, but also then the air drag. But this has a net thrust. And since I say positive, I'm going to assume here that that means that there is a positive net force in the direction that it's moving. And so as we learned way back in chapter, well, I guess it's a combination of 4, 5, and 6 put together, we learned here that this would then give it an acceleration. This thing should be going faster and faster. And in this chapter, we learned that is connected to an angular acceleration. And so I think that's where they're going to go with this. Okay, here's A. Find the torque that this net thrust produces about the center of the circle. All right, well, in our discussions last week, as we got towards the end there of chapter 10, our last discussion on Wednesday was about this quantity called torque. And we said it was made of 3 factors. Did we use a symbol theta or phi for the angle? I want to say we used theta, but I'm almost thinking that the symbol the author used was phi. Theta, all right, I'll continue to use theta. I just like to use the same notation your author uses. Otherwise, as you're studying your notes and studying the book, it makes it harder on you. How come I don't see torque even anywhere in the chapter? Rotational? Okay, oh, here's torque. Torque. Yeah, he does use a phi, so that's what I'm thinking. Bummer. All right, but shall I continue to use theta? Sure? Okay, and hopefully it won't confuse you, but maybe we should talk about the angle. What angle are we talking about here when we say the angle? And now you'll see why the author really likes the symbol phi. What angle is this referring to in this picture?
Angle between the force and the angular acceleration.
Okay, so it's the angle between those two. So this is R going out like that. This is the force going over here. So this is the angle they're talking about. Fair enough? And the reason, it didn't dawn on me last time, that the author switched his notation to a phi is he doesn't want you to confuse it with that angle, the angle of rotation. And that one we have been calling theta. And so it's easy to confuse those two. And so maybe I'll ask again, would it be better if I continue to use the theta or switch back to the phi so that you realize there's 2 different angles up here? Anybody care? No? Actually, maybe this discussion in itself was best still, that it points out there's 2 different angles here. And then we got to be careful with which one we're talking about. So that being said, we can answer A right away because we know the distance is 30 meters. We know the force is 0.8 newtons. And we know the angle, whether we call it theta or call it phi, doesn't matter. But knowing what angle is does matter. It is not some angle here measured from the x-axis. It is the angle between the R and the F. And so this is 90 degrees. And of course that hopefully makes sense. Sine of 90 degrees is 1. And so you get the most torque when you push perpendicular. That much makes sense. And then 8 times 3 is 24. 0.2, and then it would be a Newton times a meter. And so there's our first example calculation of how do you get the torque. And so it's 24 Newton meters. And again, notice the units, right? The units are a Newton times a meter, as we talked about on Wednesday. And notice I am not going to call this a joule, right? A joule is a unit that we use for work and for energy, not for torques. Even though they are the same base units of a Newton and a meter, there's a different distance involved. If you want to know the work done, then you would be talking about the distance the airplane moved, not the lever arm. And so you'd get a different numerical value because we're talking about a different distance. And of course we get a different quantity. We wouldn't get torque, we would get energy, which is why we would do a different units. Exactly. And so there is my first example of calculating a torque. Continuing on here, it says find the angular acceleration of the airplane when it is in level flight. All right, angular acceleration. Well, I think what the author would like us to do is to use Newton's second law. That is, the net torque is equal to the moment of inertia times the angular acceleration. This is our new chapter, the first time that most of you have seen Newton's second law associated with angular acceleration. Well, you touched on it a little bit in 102, but you didn't do Newton's second law with rotation nearly as much as Newton's second law of translation. That you guys did a lot in your Physics 102 or your high school physics. But the rotational stuff we kind of touched on, but now as you'll see, it's, you know, touched on it to get you ready for this class, but this class goes into obviously a lot of detail with rotation now that we've done a lot of detail with translation. Keeping that in mind, then, you can see why step A was a nice first step. There's the 24 Newton meters for the net torque. And so I've already got the torque. This is worth another discussion about the moments of inertia. And the moment of inertia, as we said, was taking the mass of the individual pieces, multiplying at the location of them, and adding it all together. And so if you remember, we started with a very simple case. Our simple case was we took this object that had 3m on one end of it and a 1m on the other, and all we did was add those two pieces together. And we kind of treated the little blobs as having all the mass at that point, until we started doing more complicated things like the hoop and the disc and the rod. Then we realized that the distribution of the mass, that is the radius, is different for different pieces on that object. But I think on this one, the author is trying to say, without directly telling you, that go ahead and treat the model airplane as being small compared to 30 meters. In other words, yes, one part of the wing is slightly a little bit closer than the other part, but by how much really? I mean, I don't know what he really means intent by the size of the airplane, because he doesn't tell us anything about the size of the airplane. And in fact, the whole idea that he does not tell us the size of the airplane gives me more reason to believe he wants us to take all the mass of the airplane as one big concentration 30 meters away, when in reality a little bit of it is a little closer than 30 and a little bit more of it is a little bit further than 30, but we don't know how much. And so I'm going to take that as a license to say he's really saying treat this airplane as a single blob that is 30 meters out. And that's great, because that makes it real easy. I've got one mass to add up at one distance. Piece of cake to get the moment of inertia. So it is a mass of 0.75 kilograms at a distance of 30 meters squared. That would be the summation of all the pieces. Well, now all the pieces is just one. And so it's the easiest moment of inertia calculation you can do. It wasn't like the real hard ones we saw on Wednesday. And then I can now grab my calculator to get that angular acceleration. So it's 24 divided by 0.75 divided by 30 squared comes out to be 0.0356. And what are the units? Should come out to be radians per second squared because I'm being asked to calculate an acceleration. Exactly. Let's check it. So a Newton is a kilogram meter per second squared. So there's my Newton times the meters. So that's in the numerator. In the downstairs, the denominator, I got kilogram and I got meters squared. So sure enough, kilogram cancels with kilogram and meter squared cancels with meters squared, and we just get per second squared, which is perfect because remember radians wasn't a real unit. It was kind of a clarifying word. So I will throw it in here to write it as radians per second squared. And so sure enough, I do get the correct units, as you should with all of our unit analysis. Stop, look at your units, right? It's a good way to confirm if you're doing anything wrong there and say, okay, I know what the answer should be because I'm looking for the quantity acceleration, angular acceleration. And so the unit should work out that way. And sure enough, it does. Now, we could have approached this a little bit different. I like this one the best because it does illustrate the rotational motion, which is what this chapter is all about. But we could have done this. Couldn't we have found just the acceleration? What I'll call the translational acceleration? And then didn't we learn that the angular acceleration is the translational acceleration divided by the radius? That was another nice little feature we learned early on in chapter 10. Let's see if we get the same thing here. And so to get the translational acceleration, I would take the net force, which is 0.8 newtons, and divide it by the 0.75 kilograms. That should give me the, what I'll call the translational or tangential acceleration, as one of you asked last time. And so 0.8 divided by 0.75 comes up to be 1.07 meters per second squared. And so that should be, again, this tangential acceleration. And so that has that step had nothing to do with this chapter in terms of rotation. Now, this part does. This part was the connection between our translational acceleration and our rotation. Let's see what we get here. This would be my 1.07 meters per second squared and dividing it by 30 meters. So divide this by 30 meters and I come up with 0.0356. And then the same idea with the units. I would get a per second squared. I'll throw a radian in there for clarification. And so sure enough, it comes out to be units of radians per second squared. And sure enough, it comes out to be the same answer that I got when I applied Newton's second law for rotation. So good. It's working. Okay. And maybe I should have even backtracked in this problem and said, again, like all these problems, you need to read them and decide, how are you going to handle this problem? Is it a rotational problem? Well, obviously, it wouldn't be in chapter 10 if it wasn't a rotational problem. That's the easy part of chapter 10. But when you hit the homework, well, maybe not the homework because you'll be doing homework from chapter 10. But when you hit the test or the final exam, those are the tough questions. You start off and say, okay, how do I do this? Do I do this with energy, or do I do this with translation? Do I do this with Newton's second law of rotation or Newton's second law of translation? And you can see in this case, I could actually approach it either way. Here I did Newton's second law for rotation. Here I did Newton's second law of translation. Eventually I had to convert it into a rotational problem at some point to answer the question, since it does ask directly, what is the angular acceleration? But again, I think you're getting the idea. C says, find the translational acceleration of the airplane in its flight. Well, I guess I actually kind of already did that by using Newton's second law here. But I think the author intent was actually for you to begin to use this equation then and say, look, there is a connection between the translational acceleration and the rotational. And so this 0.0356 radians per second squared, then multiplied by 30 meters. And so maybe I shouldn't have even done this. This is part C here in reverse. So I'm kind of undoing what I just did. But obviously if I take 30 and I multiply by that, I will get that of 1.07. And if you look at your units, you can see that I've got meters per second squared if I just drop the word radian. And so there is the translational acceleration, as this thing must be going around, going faster and faster and faster. So there's a couple of beginning ones there. How are we doing on time? Oh, good. Let's move into 47. 47 gets a little bit harder here. And it says here, an object with a weight of 50 newtons is attached to the free end of a light string that is then wrapped around a reel of radius 0.25 and mass 3 kilograms. The reel is a solid disc and it is free to rotate in a vertical plane about a horizontal axis passing through its center. The suspended object is released 6 meters above the floor. Okay, well there's certainly a lot of words there in that description. And so let's break it down, and like any of our problems from the very beginning, make sure we've got a good physical understanding and picture of what's being asked here. It'll really save us a lot of unnecessary and confusing work once we've got a good physical picture of what's going on here. And so that first part is clearly saying we have a weight, a 50 Newton weight. Again, notice they're telling me the weight of it, not the mass of it. It is attached to the free end of a light string that is then wrapped around a reel. All right, so if I understand all of those things, and there's more description there, there is a solid disc, a reel, where what I have done is I have taken a weight of 50 newtons and tied a string to it, with the string then wrapped around the reel. The reel is made out of a solid disc. It is free to rotate in a vertical plane with a horizontal axis. Did you catch all those words? I don't have anything that looks like a disc. Maybe I should have brought a disc out here. Okay, not a solid disc. But again, look at the words. They're saying it is free to rotate. Okay, so we know it can rotate and in a vertical plane. So we know it's angled this way, not this way, right? This way. And a horizontal axis. So here's the axis. And so that is why my picture looks the way it does. The axis that it can rotate is a z-axis in this picture. If I were to put the traditional X, Y grid up here with Z coming out of the board. And so I have a vertical plane of rotation, horizontal axis in the z direction. All right? So that's what all that says to me. And then they give me a bunch of numbers here. They give me a 50 Newton weight. So there's the 50 Newton weight. They give me the radius of 0.25, was it meters? Oh, I didn't look closely. 25 meters. And the reel itself is 3 kilograms. So they give me its radius, they give me its mass, they give me the weight of the hanging weight, which means I can also get the mass. I don't know if I need that, but I'm going to go ahead and even just calculate it here, because I kind of suspect I am going to need it. I know that weight equals mg, so that means the mass is its weight, 50 newtons, divided by 9.8 meters per second squared. And so it should be just a hair over 5 there, 50 divided by 9.8, and so 5.10 kilograms then would be how much that mass is. Actually, that's more mass than the reel itself, so maybe I should have made that weight look bigger there. An object of weight 50 newtons is attached to the free end of a light string wrapped around a reel of radius 0.25 and of mass 3 kilograms. The reel is a solid disc, free to rotate in a vertical plane about a horizontal axis passing through the center. The suspended object is released 6 meters above the floor. Okay, so this whole thing is done in obviously a very large room, or at least very tall room here. So we got 6 meters up there for our weight. Okay. Now the question begins. A, determine the tension in the string, the acceleration of the object, and the speed at which the object hits the floor. So again, hopefully all these questions sound very similar to a lot of questions we had in the past, although we weren't working with rotations, we were working with translation. You probably remember problems such as a weight is tied to a string over a pulley, and then there is another weight sitting on the table. Maybe the table has friction, maybe it doesn't, but we would move and this one would move down, this one would slide over, and we would ask questions simply like, how much tension is in that string? What is the acceleration? What is the speed? And those are the 3 questions that they are asking. What is the tension? What is the acceleration? What is the speed? And of course, in the past we learned that for translational motion, if they were asking for speed, that was always a nice question because we could get that by either energy or by Newton's second law. However, when they ask for acceleration, we probably should use Newton's second law. We don't necessarily have to because we could get speed, and once we get speed, we could work backwards using our kinematics to get acceleration. All right. But they asked for tension, and that's one of the forces involved there. And that was one that we needed to approach it with Newton's second law. And so simply put, here's my point. My point is, if you had a hanging weight with a string over here, and the question said find the tension in the string, you would have done that with Newton's second law. So let's do the same thing then. Let's apply Newton's second law. Now, we have rotation involved here. So I'm going to use Newton's second law of rotation, but that's what I'm trying to illustrate that you should see here. And so when we did Newton's second law, the first thing we did is we said, let's draw a free body diagram. Because when we did translational motion, we were interested in finding the net force. Of course, now we're going to be interested in finding the net torque and setting it equal to I alpha. But let's set up this free body diagram. So I would set up just the reel by itself and say, what are the forces on this reel? Well, maybe I should ask you guys to help me out here. What forces are on this reel?
Tension.
Okay, obviously the string has a tension in it, pulling it down. By the way, is that tension 50 newtons? Does the tension in the string equal the weight of the object? No. Right, we talked a lot about that in chapter 5. Well, we probably should continue to talk more about that. But there is some tension. And I'm not going to set it equal to 50. I'm tempted to, but that would be very wrong. Okay? There is tension. Any other forces on this reel? Right? Gravity. We know that one. Right? Everything touching it plus gravity. Now here's where we're going to have to invoke a little bit of chapter 9. Where is the force of gravity? Center of mass, exactly. So the center of mass of a uniform solid disk would be right at its center, right? So this would be mg, where m is the 3 kilograms. Okay? Any other forces? Well, are you saying there might be some friction in the bearings around this wheel? Is that what I'm hearing?
Inertia that's preventing.
Okay, now I agree there's an inertia, but inertia is not a force. Okay, so I don't put that in my free body diagram. Yes, it's going to show up in my equation when I do either F equals ma or torque equals I alpha. Okay, so there is inertia. Anything else here? Okay, what do you mean by normal force?
The supporting force of the axis.
Yeah, I would say there definitely is a support, an upward force. I'm going to call it F, not a normal force. I suppose we could just as well call it a normal force also, because it, is probably this metal shaft and it's pushing up. So whatever you want to call it a normal force, although I like to reserve normal force for, forces on the planes, and this axis is a circle, but it does have a surface, and so if you want to call it normal, that's fine. But the bottom line is we have to have some kind of supporting force lifting it up, right? I mean, if you did not have this force going up from the axle, obviously these two would pull the whole thing down. And that's exactly what is not happening. It doesn't move down, it rotates. And so what that would say from a Newton's second law is that this force up equals those two forces down, right? It does not translate. In fact, maybe I'll put it off to the side. That would just say if I were to add up the forces in the y direction, I would have F going up, I would have mg going down, I would have tension going down, and the idea is to have that equal to 0, so this reel does not translate. It does not go up, it does not go down, it does not go left, it does not go right. But I wasn't really even interested in translational motion. That's chapter 5. I'm interested in rotational motion. So let me add up the torques. That's the important one, not adding up the force. So let's talk about the torques. Maybe it's worth putting the equation for torque back on the board. Torque is equal to R times F times the sine of the angle between R and F. Again, whether you want to call it theta or call it phi. And so let's go through each force individually. How much torque do I get from, say, gravity? 0. Why? Because the radius is 0. Exactly. And that hopefully doesn't surprise anyone. Gravity is not the part that is making this reel rotate. I think you can just see from your own real-world experience that what's making it rotate is this string, which has that 50 Newton weight hanging from it. So the fact that we get 0 torque from gravity is not a surprise. In fact, look at the supporting force F. How much torque would you get there? 0. Why? Same reason. The radius is 0. So anything that is going to be acting with a force directly at the radius means that you won't get a torque. Those torques do not make, or those type of forces make zero torque. They do not make things rotate. They make them translate. You may say if this force was not big enough, then gravity could be a lot more than that and the thing would fall. And so if you were to take this big heavy wheel and put it on a popsicle stick, you would expect it to break. You would expect it to go down. You would expect that you don't have enough upward force. You would expect to get some translational motion. I'm going to assume, though, that whatever this axis is, it is strong enough to hold the forces that are pulling it down, so it doesn't break. So that's why the forces add up to be zero. And then the torques from those two are zero. Question?
Yeah, if the center of mass was somewhere else, then gravity would.
Yes, exactly. And so had this been a slightly different configuration, where this was the reel and we put a bolt right there, then since gravity is some distance from the rotational point, you can see that we would get a numerical value for the torque. And we would see then that gravity is part of the mechanism making it rotate. And so this one would kind of twist downward like that. And gravity is part of making it rotate, yes. But in this case, the torque is zero. And so keep that in mind. All these forces that act at the axis itself, at the rotational point, will have an R value of zero and you'll get zero torque. And then, of course, not a surprise then that the only thing making it rotate is that tension. And so I would say the torque then is the tension in the string times the radius times an angle of 90 degrees. And I guess I've got to look a little closer, but the string is going to come off as it wraps around tangentially to the circle. And so there is a 90-degree angle between the lever arm R and the force, which is the tension in the string, making it rotate. And I suppose I should ask, is this a positive or a negative torque? Because in my picture, I have this pulling it so that it would rotate in a clockwise direction. And traditionally, what do we call that? Negative. And so I'm going to put a negative torque just to stick with tradition. And of course, that really came to how you drew your picture. Because I could have drawn the weight over here and then that would have been counterclockwise. And so whether it's positive or negative isn't really that important or well defined in this problem. They don't tell us, how it is actually set up. I kind of drew my own picture. And then likewise, of course, even though traditionally we call clockwise negative, we certainly could have called it a positive. But again, since this is your first time working with rotations, it's probably best to stick to the things that you're more familiar with. And so you're used to calling clockwise negative. So let me call clockwise negative. So I will have a negative torque, which would mean I'm going to have a negative acceleration. This begins to make it turn faster and faster in a clockwise direction. A negative acceleration. So that's the sum of my torques. And that should be equal to I alpha. Okay? And so what I wanted you to see in this problem was that just like any problem that we would have done in Chapter 5 using Newton's second law for translation, I am going to do the same logic here, but I'm going to apply it to rotation. And so if you can learn that skill, you'll see how easy Chapter 10 is. If you don't see that analogy, ouch, you will see how hard and long this chapter really is. Okay? And so there would be my one problem. Let me keep going here. I'm gonna put here a negative TR. Oh, actually, I'm going to substitute in R because I know the value of R. It is 0.25 meters. And the sine of 90 is 1. I'm also going to put in the moment of inertia. You see, they were very clear. They called it a solid disk. Isn't this one of the ones we worked out on Wednesday? Do you remember the equation for a solid disk? Yeah, 1/2 times the mass of the disk, which in this case is 3 kilograms, times the radius of the disk squared. And it looks like, thank you. I even can cancel a little bit before I grab my calculator. But if I grab my calculator, then I'm going to get a negative t on this side. And over here, I'll have a 1/2 times a 3 times a quarter. And so it looks like I have 3/8. I'll keep my units hanging around. Just so that I can just kind of check my unit analysis, make sure they're still working right. But it looks like one of the meters cancels with one of those, and so I've got a meter from there and a kilogram from there. And so I'll put a little box around it, but that's really only half the problem. That's the first part of the problem, and that was to show you then that I should be doing the same logic, and you should be doing the same logic, except instead of doing translational discussions, we do rotational discussions. And so remember those 4 steps. A, right? Free body diagram. B, I guess A, sorry, 1, get a good physical picture of what's going on. 2 was that free body diagram. 3, write out the equation. And then 4, solve the equation. And we're kind of stuck there. We can't completely solve this. It's got 2 unknowns in it. It's got the tension and the acceleration, which is 2 of the 3 things that they are asking for there. So that's good that we have them in the equation. It's bad that we have 2 unknowns in 1 equation. So what else are we going to do? Yeah, and just like we did with those translational ones, right? We could not solve it by just doing a free body diagram for one of the objects. We had to also do a free body diagram for the other object. So let's do that. And that should be the easy one, because the other one just goes in a straight line. It's not our new stuff, it's our old stuff. And so let me clear this part off and say, all right, let's write a free body diagram for the other object. And so this other object would have just 2 forces on it. It, of course, would have gravity pulling it down. Let me put a capital mg there so that we don't confuse it with the gravitational force from the first object. And of course, what's lifting it up is the tension A. Let me, of course, realize that this is all translational motion. So this is not going to be a discussion about the sum of the torques. This will be a discussion about the sum of the forces. I'll call it the y direction, but also I want to make sure, just like when we did in chapter 5, that I don't confuse my signs. And so this one, when this thing rotates in a clockwise direction, doesn't it make this go down? And so that I can be careful with my signs. If I'm going to call this a negative direction, which I did, then let me call this a negative direction, which down is traditionally the negative direction, so there's nothing real to change there. But that does mean that I'm going to call the up the positive direction and down the negative direction. So I'm going to stick to the tradition here. Okay. I guess I got kind of lucky in my drawing. If I had drawn the weight on this side, then I guess I probably would have had a positive number here, but I would have called down positive then at that point, so that the motion of this reel is positive, the motion of this weight is positive. So I can keep my signs together. All right, well, using that then, I've got tension, which is a positive number, and minus gravity, which is a negative number, and that must equal to then ma. And so that is our old stuff, but we got to include it. So this is chapter 5. And so here is Newton's second law of rotation as applied to, well, the reel. Here is Newton's second law of translational motion. And so again, if I put in my numbers, you'll see what I have here. I have tension minus an mg. Well, mg is this number here. This must be the 50, right? This is the 5.1 times the 9.8. And so the weight of this thing is 50 newtons equals 5.1 A. And I'll put a box around that equation also. Because again, it has two unknowns in it, so I can't by itself solve it. Now fortunately they both have tension in there, that's good. However, that has an A and that has an alpha. So you may argue that we got three unknowns here. Okay. But my final step is, isn't the alpha and the A related? And so like we just did with the airplane on that tethered string here, I should be able to stand back and say, all right, then as this thing turns and unwinds, then the weight that is connected to the end goes down. And I would say, if this goes down 1 meter, it does that because the string unraveled 1 meter. And that's a nice way of saying that the motion of the string, which is tied to the rim, has the same acceleration of that weight. So the acceleration of this weight is the same acceleration of the rim. And there is a mathematical connection between the acceleration of any part of a rotating object and the angular acceleration based upon what is the radius to that object. And since we're talking about the rim, I'll go ahead and use the entire radius of it. Notice they could have done something like this. They could have tied the string on some kind of inner shaft, and then my R in this equation would have been the R of that inner shaft. Okay? The key to realize here in this physical picture is that the acceleration of this object going down is the same as the string, and the string is the same to whatever part of the rotating object it happens to be tied to or wrapped around. And in this case happens to be the rim. And so this is the connection between alpha and R. In fact, I should put in the number here. So A equals alpha times 0.25. And maybe I'll put my units in there. But now, that's my third equation. So I got that one, and that one. And so now I can begin to solve this equation. And maybe the easiest one to do is to just do a direct substitution right here. This says minus the tension, and according to this, rewriting this, the tension would be 5.1 A plus 50. And so this tension is 5.1A plus 50. And that would have to equal 0.375. I think I'll drop my units here and then put my alpha there. And then I can come over and either substitute alpha or substitute A. Since they don't really ask for alpha, do they? Yeah, let me then substitute for my alpha. And so this is A over 0.25. And so there's my negative 5.1A. In fact, let me do the distributive property as long as I'm here. Minus 50. And now I can solve for one of these, which would be my A. Let's see, why don't I just take that number, 0.375 divided by 0.25, that's 1.5. I'll bring this over, so I will add to it 5.1A, 6.6, and so that will leave me with my negative 50 divided by that last answer, and I get an acceleration of negative 7.5. It looks like it rounds up to an 8 meters per second squared. And so there is one answer. What's the acceleration of this object? And of course, once I have the acceleration, now I can get the rest of these. I'll get the tension right here, because the tension is the 5.1 times that negative 7.58, and then add to that a 50, and I get a tension of 11.4 newtons for the tension. In fact, that brings us all the way back to what we said at the very beginning. Does the tension equal the weight? No, not even close. And yet, I saw it a few times on the second test, maybe because you didn't know what else to do, and people just said, the tension is the weight of the object. No, it is not. And I, at least in the past, have seen it a lot on the third test. So I'm warning you, don't assume the tension is the weight of the object. It's not even close to it. Okay? And so there is the 11.4. And then, what was the third part of this question? Or what is the speed of it? Well, the speed of it, we know it goes down 6 meters, and we know its acceleration. So why don't I use the straight translational kinematics equation of that second object, which is going in a straight line. And so I think it starts from rest. Did they make that clear? Well, it says released 6 meters above the floor. I'm going to think that they're trying to tell me that we start it from rest, and then it goes faster and faster. So this is 2 times, and the acceleration is that negative 7.58, and so there's my acceleration, and it goes down 6 meters, so there's a negative 6, and so the velocity when we take the square root will be plus or minus. Since it's going down, we know it's going to be the minus 1, so maybe there's no, I shouldn't even have put the plus 1, I'll just put the minus there. But I better make sure I got both negatives there. I don't want to try to take a square root of a negative number. So they're both negative. So 2 times a negative 7.58 times a negative 6, and then the square root of all of that gives me a speed of a negative 9.54 meters per second for the speed at the bottom. And so there's a really good example problem. And if that made sense to you, then I think you're ready to start attacking these on your own. Not to say that they will go as smoothly. I think you recognize that it's easy for me to stand up here and work through a problem. And I've, at least in the past, have many students said, oh yeah, that doesn't look hard. I won't even do the homework. I'm ready for the test. Ooh. Now, there's a rude awakening when you get on the test. It is totally a lot harder to do the problem on your own than it is to watch somebody do it and say, well, yeah, I see what you did. It made sense. Okay, if it made sense, see if you would do that. And I would suggest practicing a lot before you hit the test. Right? It just looks easy till you start trying it. Okay. Well, there's a second part to this, which I think makes a good problem also, because if you'll notice, I approached this problem all with Newton's second law. But since they did ask for speed, I could have done this with energy, and that's what the second part of this problem. It says, B, verify your last answer. So this answer here for the speed, by using the principles of conservation of energy. And so let's see if we would get the same speed had we used conservation of energy. And we will. We should, unless I made a mistake here or on this next step here. But we should get the same thing. But like I said, it's why it makes a nice problem to illustrate. Even though it's kind of a long problem, it's a really good one. It's got all the pieces that you are going to be asked to do. And like I said, I just wish we had more time to do more of these. But again, long chapter with the idea, see the analogy, okay, you've already done them. And then boom, let's see how you can do them. But I will do the conservation of energy. And in this case, I guess I've erased my picture. Maybe I'll kind of redraw a smaller version of it here on the side. But there is that picture as this thing moves down and unwinds. And as I look at the energies here, I would begin to look and say, all right, what energies do I have to begin with? There's no springs involved here, but there is gravitational potential energy. And at least for this object, the one that moves in a linear motion, the one that I called object number 2, the one that weighs 50 newtons, this one, why don't I call the ground y equals 0? And maybe I should say it again, right? This is where you have that freedom of choice. You can call y equal to 0 anywhere you want. But as I write this out, mgy initial, the mg is 50 newtons, and the initial height then would be 6 meters. And they said that this moves 6 meters before it hits the floor. So if you're going to call the floor 0, then obviously it's 6 meters up. So 6 times 5 is a 30. So we have to begin with 300 joules of energy. Now you may argue about the reel itself. Doesn't it have some gravitational potential energy? Well, we can address that in one of two ways. Maybe the easiest way, though, is to say, let's call y equals to 0 for that one the center of mass of it. So that's why I don't have a term here, because it's a 0. Even if I didn't call it 0, then whatever number I would get would just show up on the other side afterwards anyways for a final energy, and it would cancel off. So in terms of the movements here, there is no change in gravitational potential energy of the reel. The reel does not go up or down, just that weight. Which is why then on the other side of the equation, I'm going to put a 0 first, indicating then that what happened is this moved all the way down, and now what was 300 joules of gravitational potential energy is now 0 gravitational potential energy. Of course, where did it go? Well, obviously that little weight is now moving. So it now has kinetic energy. But here's the nice part of this problem. Here's where the chapter 10 comes into play. What else is happening? Object 1 is rotating. And so object 1 is going to have some rotational kinetic energy. And that's the 1/2 I omega squared we were talking about. And did a few examples with kinetic energy. And so the bottom line is these 300 joules come out of the gravitational potential energy and go to kinetic energy, and it's kinetic energy of each object. One is translating and one is rotating. And so as I write this out, this would be then a 1/2, and 5.1 is the mass of this translational object. The real then has an inertia of that much, right? It's a solid disk, so it's 1/2 times the mass of the disk times the radius squared of the disk. And the angular speed, well, that's going to kind of be the same discussion that we did here with angular acceleration and translational acceleration. As we think about this reel that is rotating, when it gets down to the end, yes, the translational object, the second object, has a speed. How much speed does it have? Well, its speed is coming from the string, which is coming from unwinding at the rim of that reel. So the speed of the rim where the string is wrapped around must be the same as the speed of the object itself. And of course we learned that there is a numerical relationship between the angular speed and the translational speed. It was the angular speed times the r. And in this case, the r would represent the whole radius out to the rim. And so I am going to put a v squared over a 0.25 squared. And of course now I have like terms here. Each of these two terms has a v squared in it. In fact, this one, I can save myself a little work by realizing that those will cancel off. So this is 1/2 times 1/2, that's 1/4, that's 3/4, so I'll just go 0.75. And I should be adding that to 5.1 divided by 2. And so this is 3.3. And then this is 300. So if I take 300 and I divide it by my 3.3 and I take the square root, I get a plus or minus 9.53. And if I carried my units through there, you'll see that it is meters per second squared. Does that match what I got before, other than rounding down instead of rounding up? Yes, it does. And I suppose I should even say that I know it's going down. I guess I called down negative right here when I did gravitational potential energy. Remember, that was the condition. You can pick y anywhere you want, but you have to call down negative. So I have really already in the problem defined down as negative by using that formula for gravitational potential energy. So I must finish the problem with a negative sign, which is the same definition I used in the first part. And so there's negative. Fair enough? Good problem. A little bit on the long side. Kind of makes sense? Guess what we're going to do in lab today?
Exactly this.
Yeah, pretty close to it. Not exactly this, but it is going to be like this. And in fact, we probably need to move on now into chapter 11. Wish we had time to show you a few more examples, but 49 is probably a better looking setup of what we are going to do in the lab. Is we are going to take a weight, like that problem and this problem, and wrap it around a base here. And it's kind of like this reel, except two big things are different. Number one, the position of where the string is wrapped around are different. And we won't get this nice feature of these two R's being the same. All right, no problem there, I hope. Also, we won't just have a disc that is rotating. In fact, what we'll do is we'll first just do the disc. You see this crazy looking object on top, we'll just take that off and we'll just put the disc on there. And so we will find then what is the moment of inertia of a disc. And so instead of trying to find out what is the speed at the bottom, we will actually measure the angular acceleration, and from that get the I of the disk and see if the I matches the 1/2 mr squared. That's going to be our first big step. And then we will put an object on top. And then, just like here, we will put the object on top, we will let it fall and spin, and we will find out what is the inertia of that object we placed on top. Then the third part of the lab today is we will take it apart, and now we will take an object, and our object will happen to be a disk, and we will make the disk rotate around its center. Then we'll move it off center, then more off center, then more off center. Do you guys remember how to get the moment of inertia of something off center? Do you remember that parallel axis theorem? And so you're going to measure off center and then calculate what it should be off center and see how closely do those match. It's a really good lab. Maybe a little bit on the long side, because here's what we're going to do. We're going to go through these steps again. And so I'm glad we went through all this, but I think it's worth going through again. And so as we come into the lab, I'll say, all right, let's talk about this, and we'll go through the derivation again. And just to make sure you understand it, your last question in the lab says, go through this derivation on your own and show this is the equation. So you're going to see it 2 more times today. Once me doing it again at the start of the lab, and once you doing it on your own at the end of the lab. Anyways, hopefully all of those will help you get a better understanding of how to deal with problems involving rotation, and then how to do Newton's second law, and then of course how to handle these homework problems. So with that said, I must say we need to move on here and get started in chapter 11. As I was saying an hour and 20 minutes ago, this is a short chapter, not so much an easy chapter. In fact, by the time you put the long chapters of 9 and 10 together with this chapter 11, you are going to undoubtedly see that this is some pretty advanced and tough materials. The good side of this is definitely the hardest of the semester. I know we've been building up higher and higher and higher, and some people get to this point, they're tired because it's the end of the semester, although as I said before, I think you guys have that nice advantage of spring break. Spring break kind of, hopefully, got you rested up and ready to tackle these last 5, or I guess there's 6 weeks, counting finals week after spring break, and we already did 1. So get ready to handle these 5 weeks. And so most classes, you're getting into that real hard stuff. You've been getting harder and harder and harder. It's probably true in your math class. It's probably true in your chemistry and your computer science class and your physics class. However, we peak in our difficulty right about here. So work hard, focus on this. You'll see the next ones are easier. I won't say easy because none of this is easy, but it is certainly easier as we go into chapters 12 and 13 and 14 and wrap up the semester. But 9, 10, and 11 are definitely a real challenging set of problems. And so again, I would encourage you to make sure you give yourself lots of time to work on these. Start these early in the week. Work hard on them. Ask lots of questions. See Don, see me, see the tutors. Go to the YouTube video. Watch it again and again and again. And not the whole 2 hours. I don't know how anybody could sit there for two hours. I always tell Don, I've got the best job because the only thing worse than maybe a root canal is having to sit there for 2 hours and listen to somebody talk to you. It's like, so I'd much rather give a 2-hour lecture than to listen to a 2-hour lecture. But that's me. I get very energetic. I just can't sit there for 2 hours. So I suppose that's a long way of saying you guys should be complimented that you actually bear it out there each morning and sit through. All right, well, as I was saying here, chapter 11 is our next piece of rotation, and it's an extension of what we've been doing. And so I'm going to go ahead and make that chart again as we get started. That chart had a place for us to write down. Let's look at the equations for our translational motion and compare that to our rotational motion, because again, if you don't see that if you don't see that connection, that similarity, boy, you can just get so overwhelmed in this chapter and in chapter both 10 and 11, because they just throw it out there and say, oh, here's Newton's second law, you got it. Oh, here's conservation of energy. Oh, you got it. And it's not quite so simple as you see here. The one thing that we have not done is momentum. Kilogram meters per second was our discussion about translational, or what we'll now call linear momentum. It was mass times velocity. It was chapter 9. And so we have to have a rotational, or what we will call an angular momentum. And so we will fill in that chart here in the 35 minutes that we have left here. What is angular momentum? Well, I think we'll get that far, but even before we get to that, we are going to have a little math discussion. Let me introduce you to, if you have not already, what we will call the cross product. If you recall, we said when we got into chapter 3 that we needed to understand vectors before we went further. But all we did in chapter 3 was add and subtract vectors. That was very useful when we got into chapter 4 and had two-dimensional motion. It continued to be very useful when we were adding up forces. It wasn't until we got into chapter 7 where we needed to multiply vectors. We did a dot product. You remember that? And at that point I said that's not the only way to multiply vectors. There's another option called a cross product that, again, you probably have seen somewhat in your math class. And so if I took, say, the vector A and the vector B, then I can take these two vectors, A, and multiply them together using the X symbol, the cross symbol, not the dot. And maybe just as a quick comparison, if I did A dot B, if you remember from chapter 7, we said the nice thing about the dot product is it gave us this piece of the puzzle. It gave us how much of B is in the same direction as A. In your math class, you probably called it the projection. How much of B is projected onto A, and then you were multiplying them together. And so when we did this dot product, we said you can think of this as how much of B is parallel to A, or mathematically it would be A times B times cosine of the angle between them. Okay, so what is a cross product if that's a dot product? Well, a dot product is kind of asking a little different question. It would be the other question, right? It would be saying how much of B is perpendicular to A. And so A cross B would be saying A multiplied by how much of B is perpendicular. Not how much is parallel, but how much is perpendicular to it. You can see mathematically that means A times B times the sine of the angle between them. And so right away you begin to see there is something very different about a dot product and a cross product. And the first thing that we see is that we use a sine of the angle between them instead of a cosine. And of course what that means physically is this one is telling us how much of the second vector is perpendicular to the first. That's what's important. Whereas over here, this is saying how much is parallel. And in fact, let's go back to torque for a moment. In this last chapter, how did we define torque? I mean, we had this equation, but didn't that come from a little discussion that we had last Wednesday, that if we took this bolt and you put a little wrench on it, and let's say you were going to tighten this bolt, you might grab the wrench here, you might apply a force like this. But if you look at that force, and maybe I'll just say right there, if you look at that force, you can visualize this force as made up of how much is in the same direction as the lever arm and how much is perpendicular, right? And as we tried to say when we were working this out, isn't it only this part of the force that makes the bolt turn? This part of the force is useless. In fact, if your goal is to tighten this bolt, you're wasting effort by pushing in this direction. You should be pushing perpendicular to the wrench so that all of your force is going to torque. All of your force is making it rotate. Probably nobody would ever grab a wrench and push it just like that. It's never going to tighten or loosen the bolt. And so the only part of the force that is relevant to twist is the perpendicular part. Exactly. That's why this mathematics of cross product is very useful in dealing with torques and is very useful in dealing with angular momentum. And so obviously we could have had a discussion about a cross product in the last chapter, but since it is really important when it comes to angular momentum, and we can kind of avoid it with torque, your author has decided, let's, and probably because there's a lot of other things in chapter 10, says even though we could have talked about torque in terms of a cross product, let's hold off until this chapter. Well, here we are getting a little more educated. In fact, I would say your author spends really 3 chapters in helping you get acquainted with torque. He introduces it to you in chapter 10. We extend on to that here in chapter 11. And in chapter 12, we do some really robust problems with it. And you will really get a good feel for torque by the time you finish chapter 12. Or you won't finish chapter 12, one or the other, because you can't get through chapter 12 until you go through all that. And by the way, chapter 12 is the easiest of these four. So again, we've hit you with some hard ones. But I think the best part about this is that we get the hard ones first, give you more time before that test. Ooh, did I use that word test? Oh, when is your test? And so it's the 27th. It's 2 weeks from today. So we'll spend this week doing 11 and next week doing 12, and then we'll have the test when we come back on that Monday. Okay? And so timing's perfect. It's laid out well. It'll be on a Monday, so we can use the overflow room over there. And so it's coming. And like I said, this material is hard. So that's another way of me saying, don't put it off till next week. Then you only have 1 week to learn all of this. Learn it now. Hopefully you did a lot of chapter 10 already. And the 9 and 10 are, you know, maybe not completely understanding of them, but you've come hopefully a long way in there. Because now you got 2 weeks to keep learning those, plus just the 2 small chapters, 11 and 12. All right, well, back to this discussion on torque. All right, so again, this equation for torque is set up perfectly for a cross product. And so from here forward, we will stop writing torque as R times F times sine of the angle. Why don't we write it as R cross F? And so this description, this mathematical description, means those three. Just like this mathematical description meant those three. And so we went from writing it like this at the beginning of chapter 7 to writing it like this at the end of chapter 7. Same thing here. We first introduced you to torque this way. And probably most of the time when we go to calculate a torque, we're going to be writing it that way anyways. But we will write it in our equations as a cross product. So I will come over here and for the first time in our chart, write torque as R cross F. Okay. And so that is our analogy to a force. And of course the units are Newton meters. Exactly. Now let's keep talking about this mathematics, because I have shown you only one of the 2 differences between a dot product and a cross product. I mean, so far I have shown you the most important difference, I think, although both are important, is that the dot product tells us how much of the 2 vectors are in the same direction, whereas the cross product is telling us how much one vector is perpendicular to the other. But it does one more thing here. A cross product gives us a vector, not a scalar. When we did the dot product back in chapter 7, we just said that if you took these 2 and you multiply them, you will then get a number, end of story. Here, not end of story. Here, when we do a cross product, this right here is the numerical value of the vector. It is the magnitude of the vector. The next step is it must have a direction. Well, again, more reason why you can see it's nice to now write torque as a vector. Let me come over here and put vector. Because we learned that the acceleration is net torque divided by the moment of inertia. What we didn't focus too much on, and we will now, is it has direction. And so just like acceleration has a direction that is the same as the net force, angular acceleration and torque each have a direction. And although we didn't talk much about the direction of the torque, we certainly talked a lot about the direction of the acceleration, or maybe I shouldn't say a lot, but a reasonable amount. Let's come back to this wrench here. All right, so here's this wrench. I grab it and I pull it this way. That supplies a torque. I think you can see already, wouldn't it make the bolt rotate this way? Which we'd call a negative rotation. It's a clockwise rotation. So what we're going to say is this has a negative Z torque. It rotates around a Z-axis. The negative meaning it rotates in a clockwise direction. If I were to take the wrench and push it that way, then wouldn't I get a positive torque? And so this torque has a direction. In those cases, they are all a rotation around the Z-axis. But if I were to take this wrench and maybe take it out of the board and put it in here and pull it down like this, then there would be a rotation in this way. That would be around the X-axis. And as I stand here and look at it, it would be a clockwise rotation. So I'd call it a negative rotation on the X-axis. Now, we said we're going to keep it as simple as we can here at the beginning, and we're only going to rotate around one axis. And so we're going to stick to that. And so all of our rotations we'll just call Z-axis to keep it simple, but that, you know, obviously later on in your education you're going to get more complicated. Objects can rotate around an X-axis and a Y-axis and a Z-axis all at the same time. But in our case, let's just talk about a Z, a positive and a negative Z. So pulling the wrench this way, I would call that a negative Z. Pushing it that way, I would call it a positive Z rotation. Okay? And so my torque, as I'm trying to say here, has become a new formula, and I really still haven't gotten to angular momentum, which is what this chapter is about, but I believe it or not, I am building up to it because angular momentum has to do with a cross product. And so you need to understand cross products, and that's why I said we're going to start here by reviewing cross products. And even though we will need them for angular momentum, they also are very useful in calculating torque. So I'll say it again, kind of a step up from the last chapter. We are now going to start writing torque in this form, as a vector, as a cross product. Sometimes this is called a vector product for just that reason, because you got two vectors, R and F, and when you multiply them together, you get another vector. So you get not only the magnitude of that vector, which is what we'll do a lot of times, right here, it gives us the magnitude, but then we will also get the direction. Here's a simple way of getting the direction. It's called a right-hand rule. As I said, we had one at the beginning of chapter 10. We used our right hand to get the direction of rotation. Remember this big wheel that was rotating? And I said if you were to take your fingers and curl them in the direction that the mass was rotating, your thumb would give you the direction. So that was one right-hand rule. Don't forget it, but I'm going to give you another one. This is what I'll call the right-hand rule for vector cross products. It works simply like this. If you take two vectors, which in this case, let's call it, well, actually let me start back here. Let's call it A and B. Take your right hand and put your fingers in the direction of the first one, A, and close it towards B, and then take a look at what direction your thumb is. And we'll call that the direction of the cross product. So here, A cross B, which I will call vector C, would be an arrowhead that is coming out of the board. It's hard to draw an arrowhead coming out of the board. So I grab this. And so here is our cross product. If this white one is A and this is B, fingers start off in the direction that's listed first, A. Close towards B. Take a look at your thumb, which in this case is coming out of the board. Here's how we tend to draw them coming out of the board. We draw it with a circle with a dot. Doesn't really look like an arrowhead, but you can imagine if somebody was shooting an arrow at you. Hopefully that has never happened, but it might look like a circle with a dot. And so there it is coming out of the board. Yeah.
Is this the same as the left-hand rule in magnetism? No.
There's a lot of other rules, but if you mean the left-hand rule for cross product, I would say it could be, yeah. Yeah, but there's other rules, just like there's other right-hand rules. So, but what you're saying, yes. And there's a lot of ways of saying the same thing. And it sounds like you're saying it with your left hand, which is fine, but I'm just going to use the way the book does. I'm going to do right hand. Okay? And so in the case of the right hand rules, we have lots of them. Remember to always use your right hand. And as funny as that sounds, I've seen students during the stress of a test, they're so busy writing away that they forget to put down their pencil, and instead they start doing the right hand rule with their left hand. And everything comes out backwards when they're all said and done. So if you're right-handed, put down your pencil and do the right hand rule with your right hand. Okay? If you're left-handed, I guess you have an advantage. You don't have to put down your pencil. You can keep writing and still use your right hand to do it. Okay? But again, right hand rule. Notice this. What would happen if I changed the order? What if I put B cross A?
Make it opposite direction.
Yeah. The magnitude is still the same. I mean, you're still going to have the same angle between them. You're still going to have the same magnitude for A and the magnitude for B. So in terms of the magnitude, it doesn't change, but direction does. Because if I take my right hand here and I stick my fingers in the directions of the first one listed, which is B, and I adjust it so that I can close my hand towards A. So I don't want to do this. I can't close towards A. I certainly don't want to do this. I'm not going towards A there either. So I've got to kind of put my fingers in the direction of the first one and kind of adjust my palm, which in this case is this way. So I'll close towards the second one listed. And then look at my thumb. Which way is my thumb pointing? Yeah, into the board. I'd call it a negative Z direction. And so I'll put a circle with an X. And you can kind of see it here. If I have the first one listed in white, then I would have the white cross towards the black one, and I would get into the board. And so this is the B cross A. So switching the order switches the sign. Instead of being positive, it's negative. It's kind of like subtracting two numbers. If I had 5 minus 3 and then I switched the order, what would I get? The negative of what I started with. So the property of cross products is like the property of subtraction. The fancy word is they anti-commute. They don't commute. Commute means if you change the order, you get the same thing. Addition does that. But subtraction is anti-commuting. If you switch the order, you get the negative of it. And that's what this is. This has the property of anti-commuting. And so the direction of the resulting vector, it's important of which one you label first. And so let's come back to torque here for a moment. Notice I have listed it as R cross F. Notice I listed R first and then F. So let's look at this wrench here for a moment. Where's R? Well, I guess here's the pivot point, right? And so here's where I'm grabbing the wrench. So there's R. And there's F. So if I were to apply the right-hand rule, and I should say right-hand rule for cross products, okay, I would take my right hand and I would put my fingers in the direction of the first vector that is listed, r. Okay, there's r. So r is something like down that way. Now I don't want to close my hand now because I would not be closing it towards the F. So I need to rotate my hand, I guess here, because then I got my fingers going down and I can close towards F, can't I? And which way is my thumb? In. And in is negative, right? So this tells me that I get a negative torque. Of course, you already told me that earlier. You told me if you were to pull on this wrench, it would rotate in a clockwise direction. That is a negative torque. So you already realized it was a negative torque before I went through all this right-hand rule stuff. But that's what I'm trying to get you to see, that you can use this right-hand rule to get you to the point of what direction is the torque. This one is so obvious that it's going to be a negative torque that I'm not sure any of you would need to go ahead and use R cross F to figure it out. But some of them aren't so obvious, and so you need to put your fingers in the direction of R, close towards F, and see what direction your thumb is. How about, as I said a couple times, what if I push the wrench that way? Well, again, I would put my fingers in the direction of the first one, R, and then I would adjust my hand, keeping my fingers in the direction of the first one, so I can close it towards the F. So R cross F. Which way is my thumb pointing? Out of the board. That's a positive direction. And so sure enough, this does rotate it in a positive direction. And so hopefully, between going through all of this, you begin to see how writing cross products can be very useful. Cross product means there's two parts to it. One is the magnitude of the cross product, and the other one is the direction of the cross product. And so those are the two big steps we're going to have to do when we do a cross product. When we did a dot product, it was just, hey, let's find the magnitude of the dot product, because that's all it had. It was a scalar. But here, a cross product has both a magnitude and a direction. And I'm hopefully convincing you that one reason, not even the big reason, but one reason we care about a cross product is it makes writing torques really nice. We can write them as vectors, and now we can get the direction of the torque. So not only can we get the magnitude of the torque, we can get the direction of the torque. We can decide whether it is going to rotate it clockwise or counterclockwise. And if we have a bunch of torques, then we know whether to put a positive sign or a negative sign. Because remember, to do Newton's second law, we have to add up all the torques. And so we might have torque 1 and torque 2 and torque 3, and so we have to add them up. And we got to decide, are they all positive? Are they all negative? Is 2 of them positive and 1 of them is negative, or any kind of combination thereof? And so we've got to add up our torques. And to do that, we've got to assign a positive and negative direction, clockwise and counterclockwise direction. And so, like I said, it's the cross product here is very useful for just that reason. All right, well now I think we are finally ready to get to what this chapter is focusing on, which is now angular momentum. And so let's look at the definition here of angular momentum. And maybe I should just say, let's start with looking at a single object, a simple particle that has no size. So again, you might recall that that's what made chapter 9 harder than any of the previous chapters, is we let our object have size. So let's start simple. Let's look at the angular momentum of something that is just infinitesimal small in size. Then we'll make it bigger. I don't know if we'll have time today to make it bigger, but definitely on Wednesday we will. here is going to be our definition. You can almost guess it, I think, because you know it's going to have momentum in it. You can kind of see that. What was the difference between force and torque? Was this extra R. I don't have it listed here, but the difference between inertia and rotational inertia was actually 2 extra R's instead of just 1 extra R. But there's an extra R in here. But our definition of angular momentum is going to be this. We are going to take then the linear momentum and then cross it with the radius of rotation. So then we will have angular momentum. And so let me start there. And then also notice then that the symbol we are going to use for angular momentum, coming from the Latin, is an L. And so that's my beginning step here in trying to teach you what is angular momentum. And at this point, it's just a definition to you. But hopefully you will see, and we don't have much time left today, but after Wednesday, you will see why this is such a useful and powerful definition. And of course, you can see it's defined with a cross product. So you can see why we took the last 20 minutes or so, and your author takes the first section of this chapter and says, hey, what is a cross product? Notice that a cross product gives you both a magnitude and a direction. So again, this is going to be our definition of angular momentum. Let's talk about the units before we leave this definition and begin to see how we would even apply it, before we see why it is a very useful definition. Well, what units would you get, say, for that? Meters, right? It's distance. What about this one? Well, that's our kilogram and meters per second. So when we put those two together, we get kilogram meters squared over seconds. And so coming over here in my little chart, I can put kilogram meters squared over second. And so that, as I said, is going to be a very useful definition. Now, I'll keep going here. Why don't we ask maybe the easiest question of all? That is, what would be the angular momentum of a small, single particle object moving in a circle? I grabbed this as I was coming into class purposely, because I said, okay, what if I were to take this and swing it? Actually, maybe I'll do it this way. What's the angular momentum? In fact, how does it compare to the angular momentum like this? Yeah, I would think one would be positive and one would be negative. Why don't I draw the first one? The first one, which way was I spinning it? This way? Was it counterclockwise for you? Was it? Okay. So here I had a mass m moving with some velocity v at the end of a string of radius r. Okay? And let's just forget gravity. I probably went a little faster and slower because of gravity. That's why I started to swing it above my head so it wouldn't have gravity. But I wanted you to see it. So let's just say it's swinging in a circle. It keeps going the same speed in a circle. It's not going faster or slower because of gravity. My first question for you is, could you calculate the angular momentum of that? I bet you could, right? I mean, you know what R is, you know what a cross product is, and you know what P is. So let's put that in here. I guess I would first write it as R cross P. Maybe the first thing I would do is, let's just solve for magnitude. Remember, when we do a cross product, there's two pieces now, right? There is the magnitude of the vector, and then there is the direction of the vector. All right, let's just do magnitude. So this would be r times p times the sine of the angle between r and p. Well, r is the radius of that circle. That's an easy step. That's why I did this one first. What's the momentum? And I should say the linear momentum is mv, right? Oh, what's the angle? Yeah, good. I'm glad you guys are seeing it, right? The angle, we got to be careful with. I know I'm going to put it at the angle theta, but remember, in a cross product, what we mean by this angle is the angle between these two vectors. So I do not mean this angle. What angle do I mean? Well, there's r, and there's p. And that's the angle between them. And as you pointed out.
It's always perpendicular.
Oh, it's not always going to be perpendicular.
Oh, no?
No, it is this time. Because I told you this is the easy one. Okay? And so we've been doing a lot where the torque has been perpendicular. That is, the F and the R have been perpendicular. Here, my first example of angular momentum, R and P are perpendicular. That will begin to change, okay, as we get to harder problems here. And of course, this reduces then to L equals to mvr. Maybe I'll just put a little dotted line around it. It's a useful one. But I wanted to do this one first because I think you've seen this. This is what most people see in a physics class. I know you guys who took 102, this is what your book has for the angular momentum. It has in it the special case angular momentum. I know if you had me for the 102, there's always a homework problem I like to assign about the planets going around in a circle. It has something like Mercury, and it goes around and blah, blah, blah. Now I can't remember the whole problem. And I think Dr. Kelly had the same problem. I don't know. Either way, it may have been so long ago you don't exactly remember that particular problem. But the point is, the easy case for angular momentum is to say it is equal to mvr. However, as you will see, that is way too simple. We really need a cross product. We really need an angle between them. But this would be for a nice uniform circle only. How about direction? What direction would it be? Well, here's where I'm going to take my right hand, and I am going to put my fingers in the direction of R. There it is. I'm going to adjust my hand, always leaving my fingers in the direction of R, so that I can close it towards P. And so what direction is my thumb pointing?
Positive.
It's positive. So if I were to write this as a vector, it would have a magnitude of mvr. It would have a direction in the z-axis. And we haven't used it much. Would it be okay if I put k hat now? What did I hat mean? X direction. What did j hat mean? Y direction. What does k hat mean then? The z direction. So it's I, j, and k. And we did it a few times in chapter 6, but not too much. It wasn't needed nearly as much as it's going to be needed now. And so we will say that I have a positive direction for the angular momentum. Now let's go back to chapter 10 for a moment. In chapter 10, we said you can get the direction of its angular velocity. How did we say to get a direction of its angular velocity? Well, we said just take your right hand. Take your right hand and curl your fingers in the direction the mass is moving. What direction is my thumb pointing? Positive. So this is hopefully you're beginning to see that the direction of the angular momentum and the direction of the angular speed are the same, aren't they? And hopefully when we're done with this chapter, you'll go, yeah, not a surprise. They should be. So just like for translational motion. In translational motion, the direction of the velocity and the direction of the linear momentum were the same. We could say the same thing about rotation. That the direction of the rotational speed and the direction of the angular momentum are the same. And in this case, it's a positive z direction. How would this problem change if it was rotating the other direction? What if it was rotating this way? Yeah. And so I still would have written it as a cross product. When I go to calculate its magnitude, I would write it as an r, a p, and a sine of the angle between them. That would still come out to be mvr. And so the magnitude of the angular momentum would still be the same. But what would I get for the direction? Negative. I mean, let's see. So I'm going to take my right hand, and I am going to put my fingers in the direction of R. I am then going to adjust my palm so that I can close towards the P. And which way is my thumb pointing now? Yeah, good. Into the board. So that's a negative mvr in the k hat direction. And so I would have an angular momentum that is into the board. Now that doesn't surprise you. Let's go back to chapter 10. If I were to ask you what is the direction of the angular speed, what would you have done? You just said, well, it's rotating around in a clockwise direction. Clockwise is the negative. So the fact that it has a negative speed coupled with the fact that it has a negative angular momentum, they're both in the negative z direction, is a good thing and hopefully not a surprising thing. And so this cross product, as you're beginning to see, is beginning to show its usefulness. It allows the direction of the velocity and the direction of the momentum to be the same. Just like they were for translational, they are also going to be that way for rotation. So it's a little harder definition. The math is a little bit harder. So just the concept of rotation together with the math of rotation be a little bit harder is, again, why I think the hardest part of this semester really is 9, 10, and 11 here as we work on these. So I'll stop now because we're out of time. But more on this on Wednesday. And let me say the same thing. Work on these. We're 2